Hi, good afternoon. My name is Keira Harris. I'm in Organic Chemistry 1, Section 1020. Today is November 22nd, 2025. So today I'm going to be talking about warfarin, which is a chiral molecule that's one of the most widely used anticoagulation medications in medicine. It's a great example of how molecular structure and specifically chirality can directly affect how a drug works. So as you can see on the screen, we have warfarin here. The molecular formula has 19 carbon, 16 hydrogen, and 4 oxygen. As well as you can see the IUPAC name for warfarin. Brand name is Coumadin, and medical uses include preventing deep vein thromboembolisms, pulmonary embolisms, atrial fibrillation, mechanical heart valves, and postoperative use. As you can see from this photo, warfarin has a couple of different functional groups. The hydroxyl group, a ketone, a phenyl group, the coumarin ring itself, and the carbon-to-carbon double bond. So this photo just shows the structural formula of coumarin and its chiral derivative warfarin. So when talking about chiral centers of warfarin, it actually has two, which are located at the 8 and 9 positions. So determining the RS configuration, priorities need to be assigned to each group based on the Kahn-Ingold pre-log rules. So for the 8 position, priority 1 is the phenyl group, priority 2 is the ketone group, priority 3 is the carbon connected to the ether group, and priority 4 is the hydrogen atom. The order of priorities is clockwise, and the lowest priority is group H, and is pointing away from us, so the configuration is R. For the 9 position, priority 1 is the carbon connected to the ether group, priority 2 is the carbon connected to the ketone group, priority 3 is the phenyl group, and priority 4 is the hydrogen atom. The order of priorities is counterclockwise, and the lowest priority group H is pointing away from us, so this configuration would be S. Therefore, the chiral centers at the 8 and 9 positions have R and S configurations, respectively. In warfarin, the S enantiomer is 3 to 5 times more potent as an anticoagulant than the R enantiomer because it binds more strongly to the enzyme target. The body metabolizes them differently as well. As mentioned earlier, warfarin is used to prevent and treat blood clots such as DVTs, PEs, and AFib. This is a picture describing the mechanism of action with warfarin. It inhibits vitamin K epoxide reductase, which is the VKOR. It's an enzyme involved in the activation of clotting factors 2, 7, 9, and 10, as well as protein C, 7, and Z. By inhibiting this enzyme, warfarin prevents the conversion of vitamin K epoxide to its reduced form, which is required for the activation of these clotting factors. This results in a decrease in the blood's availability to form clots, making warfarin an effective anticoagulant. In conclusion, this is warfarin, a single chiral carbon with 2 enantiomers that differ in potency, a handful of important functional groups, and a mechanism that has saved millions of lives by preventing dangerous blood clots.